matrices. So, there's proportions yesterday, right? And I don't know if I said it or not, but what I meant to do is for even numbered problems, because you can't check those answers, that I would give you what those answers were, in case you wanted to do anything about them. So 5 is to 13 as 17 is to, we did this yesterday, what did we come up with? 5 is to 13 as 17 is to what? 54? Okay. And then for question number 4, it was n over 4 is equal to 20 over 48. And we ended up with, was it 1.6 or 1.4? 1.6. That sounds right, 1.6. And then for number 6, we did this one as class 2, didn't we? Or we got started with it? 3 centimeters is to 200 kilometers. As, so if you set it up, it would go like this. X is to 4, oops, not a decimal, 417. What did we end up with for this number here?
Oh, that one. Oh, we're 6.25.
Is it 6? Yeah, 6.255 is what you said. You have that feeling. And then for part B, if you have 9.4 and we need to know the distance, it'd be 3 over 200 is equal to 9.4 over x. If you cross multiply, and then you cross multiply this way, if you divide that by 3 and you divide that by 3, you must be, what, a little bit bigger than 600? Did you finish this one? What did you get for an answer?
I got 626.
626, it sounds about right. And then, let's see, number 12 was also, so did you guys do number 12?
I have questions for 9, 11,
9,
12.
11, and 12.
Same.
You did not do 12, looks like you started 12. Okay. 9, 11, did you do 12? No. So what about 12 made this look more challenging? What's down here in that denominator? 3p plus 5? Okay, we need to know what p is. So why is this one more challenging? For any of you? Tell me, why does this look more challenging?
Because there's 2 variables.
Variables are twice, aren't they? Yeah, so it's not straightforward like this, where when you write your equation, you just have some variable on one side of the equation and everything else. But you still go through the same mechanics, just go through the same steps. So if you take and multiply 12 times the 2p minus 3, and just write it out. And then just take it one step at a time. Don't think, oh geez, I gotta get the whole thing figured out in one step. The days of math like that are over. Of just doing a math problem in one step and knowing what the answer is. That's simple stuff. It's elementary. Now you're solving or attempting to solve more complex problems, more complex issues. It takes more time. Think about it, when you're in kindergarten, what was the biggest problem there was? Getting to the bathroom on time. Not spilling your milk. Those are simple problems to deal with. Now it's more complex. So that's equal to 5 times 3p plus 5. So now you gotta get p alone. So, you know, in previous chapters, you were given problems that would look like this and you had to solve for p. And I recognize that we didn't all master that skill. So now we gotta use it. So what do? We just keep working on it, keep working towards mastery. Eventually it'll come along. If you don't give up, it'll all come along by the end of the year. So just look at this line. What's the first step that has to be done to get the variable p? You gotta distribute. So you've got 12 times 2p, subtract 12 times 3 on the left-hand side. What do you have on the right-hand side? Can you do 5 times 3 right away? 15. And 25. So this over here is 24p, right? And that's 36. Okay, so this is equal to that. Now what do we have to do? Yeah, get all the p's on the same side. Usually go for, I mean, you could subtract 24, but then you'd end up negative on the other side. We don't want that. So subtract 15p from both sides. 24 subtract 15 is 9p minus 36. That 0 cancels. That's 25. Now what? Don't divide yet. Don't divide until all of the addition and subtraction is gone.
Add 36 to 25.
Yeah, add 36, because that's a subtraction. You see, if you think of that subtraction as plus and negative, then a negative 36 and a positive 36 will zero out. 0 cancel. So, what's 36 plus 25? 61. Well, that's not a nice, pretty number, is it? No. So what, when we divide by 9, that's what p is. 61 ninths. But that's okay. You don't have to do a whole lot with it right now. I think all they want to know is what p is equal to for this problem. Yeah, so you're solving the proportion. So what that means is if you put 2 times 61 ninths minus 3, and then you had 3 times 61 ninths plus 5, if you found what that fraction was, if you simplified it, it would be a fraction that would equal to 5/12. So 2 times 61 is 122 divided by 9 minus 3 is, that's going to be a goofy number. And this here is going to be 1 over 3, so it'll be 61 over 3 plus 5. It'll be a goofy number. It's going to be a different fraction. But it still is going to have a ratio of 5 to 4. So this is still 5 to 4. So that was 12. Okay, so then the rest of them are odd-numbered problems. What else would you like to ask? Or was that the only one you had questions on? Any other questions? What's that? Number 9? Okay, we can do that. 9 for you also? How about you? Number 9, you started it or you did it? Okay, 9 is a question over here.
9 and 10.
9 and 10?
Wait, 9 and 11. We didn't get 10. Got it.
Couldn't understand it. Let's see here. Well, let's see what 9 is. Oh. The restoration of gray wolves in Yellowstone National Park in 1995. And the recovery plan called for introducing 10 breeding pairs. How many is that? 20. 20 wolves, breeding pairs. Each year for 3 years. So that's 60 wolves, yep, 20, 20, and 20. So suppose that in 2000 the scientists recaptured 14. And 3 of them had tags. So when they put them out into the field, I guess all 60 of those were probably tagged, right? That would make sense. And then, so why would they go out and capture wolves and count how many are tagged? Well,
See if the population is growing.
see if the population is growing, yeah. Because if all they catch are tagged wolves, there's probably no new ones out there, or very, very few. So with that problem, I guess we could look at it like this. There were 3 that were tagged out of, how many?
14.
Out of 14. So that's the ratio of tagged to not tagged. So if I wrote another fraction of tagged to not tagged, how many did they put out into the field?
60.
They put 60 tagged, and then this would be like the total. I think that would be a way to go. So so if they recaptured 14. So 3 out of 14. So this would be 60 out of the total. So what this is doing is this is saying that if you go out into the field and this represents 14, there's going to be 1, 2, 3, which are tagged. But now if you go out into the field and you say, well, if I could see every single wolf, there's probably more than 14 wolves, hopefully. If we assume that these are all still alive, there's a big population out there of which so I need to have 60 dots. I don't know how many that is. But if let's say that's 60 dots, this is going to be a much bigger total population. Just like 3 tagged comes from a bigger population of 14. So we can just say that those are equal. The ratio of tagged to total, or the fraction of tagged out of the total, is going to be like this. That's assuming all of them lived. Do they say that they all lived? Yeah, they don't say that, but I think we're assuming that they all live, and they know if they don't. So in the real world, if they found 10 dead ones, because they go and they radio color these things too when they put them out like this. If they found that there were a certain number that were dead, then they would change this. So all we have to do with this is rewrite the cross product, and then divide both sides by 3. So the t, so we can simplify 60 over 3 first. What's 60 divided by 3? We're going to take 20 times 14. What's 20 times 14? 280. So we believe that this is a whole population of 280, of which 60 are tagged. And that's one of the tools that they use. That's one of the tools that they use here for bears too. Have a certain number that are radio collared and they're tagged. And then you talk about when they see them, or if they get removed from the population for one reason or another. And then they use that frequency of how often they see them. They don't necessarily trap them, but just by seeing the animals over and over, they have formulas that they can use that are similar to this idea that tell us how many total animals we have. Okay, so that was 9. And 10. 2 numbers are in a ratio of 9 to 5.
Wait, we didn't get 10. I accidentally said 10 instead of 11, but I just figured out 11. So.
Oh, okay. 11 is just like 12, isn't it?
Mm-hmm.
So you have to apply the distributive property. Okay. What's the wettest place on Earth? It's in Kauai, yeah? Waila. Waialeali. Waialeali. Mount Waialeali. What's that? Is that how you say it? Waialela. It might be Waialela. I don't know why. I just have a hard time with it. But you pretty much pronounce everything. But that's Waialea. Yeah, Waialela. Waialea. Okay. So, shall we move on?
Is it supposed to be your baby?
It's supposed to be a baby. Yeah, it looks like a little man, doesn't it?
Yeah.
Receding hairline and everything. It's an ugly baby. Then let's just do this. It says try to draw a picture of yourself on a piece of paper, but let's just take a look at this one here. What I want to do with you with this is not necessarily follow exactly what they have here, but I'd like you to take a look at these two drawings. This is supposed to be an infant relative size on the left and then an adult. I mean, how does the head to the body ratio compare?
It's too small on
The man looks too small?
the it looks
Does it look a little small? Which one seems to have a bigger head compared to their body? The baby has a huge head compared to its body. Look, I mean, what fraction of the body height in this drawing is the head? I think is that 2/8? See, I don't know if this is gonna work. Who's virtual right now in this class? Griffin and Grace is in the other, she's in the other paced class. Griffin,
Sophia,
she's in the other, no, she's homeschooling.
maybe this is that.
I think it's just Griffin, because you're back now. Yeah, Dawson's in Montana, he's in his own class there. Okay.
I already missed them.
I think you joined us.
So you say that this is 2 out of 8? What about here, what is it?
1/8.
It's 1 out of 8, 1 out of 8. So the head's not proportional to the body, is it? Not equally for both of these. This might be a little extreme, this looks a little small. I think it's a little small. I don't know, stand up. Stand up. Look around. You guys too, you can play. Look at a person's head, and then say, well, there's 1, 2, 3, 4, 5, 6. How much? Here, put your head in between my fingers. There's 1, 2, 3, 4, 5, 6,
Oh, what we were,
7. You understand what I'm doing? 5? Trenton, his head is 5?
It was.
it actually, oh, never mind.
I get really close to 1/7 of your total height is your head for most of you guys. So this is 1/8, so yeah, you're right, the head looks a little small, doesn't it?
I mean, patient.
So if we were to compare these here, does the infant look similar to the adult? No. Do any of you have a little brother or sister?
Yeah.
Like little, how young?
I don't know.
I mean, I don't mean like a 6th grader, I mean like a 2 or 3-year-old?
Oh, no, mine's 8.
8? Anybody have a 2 or 3-year-old? You ever babysit? You ever watch little kids? When you're around like a 2-year-old sometime, or a 3-year-old, tell them to touch their hands on top of their head. They can barely do it. Because their head is so darn big compared to the rest of their body.
They got a lot of fat on their arms.
Yeah, they got fat in their arms too, but they can't hardly even touch. When they do this, their hands and their arms are tight against their head. It's kind of weird, but it is that way. So infants and adults are not similar in size in relationship to their body parts. So they're not what we call similar figures. Similar figures have the same ratio for all of their sides. So, for example, if we did triangles, we like to do triangles a lot because we work with triangles in terms of angles and side lengths, and we can name them. You know, we can call them things like, let's see here, I'm gonna make this a little different so we can see it. So, you know, like we have isosceles and equilateral and stuff like that. What's the characteristics of an equilateral triangle?
All of them, all sides are
All sides are equal. So does that look equilateral? Assume that it is. Assume that all these sides are the same. And if we put a single mark through, do you remember this kind of stuff? You put a mark through, that means that they're all the same length. We can do that with angles too, right? Well, what if I made another equilateral triangle like this? And then all of these sides are the same length as well. So if let's say that each of these are a length of 1, and each of these are a length of 2. What's the ratio of the small to the large? 1 to 2. It's a 1 to 2 ratio, small to large. So we could say that it's like this right here. Now, let's back up. Let's take away information. Let's say you didn't know that these were 1, but you knew they were all the same. And you didn't know that these were 2 here, but you knew that they were all the same. Well, because this is a 1 to 2, everything here has to be a 1 to 2 because they're similar figures. So similar means the same shape, but not size. Not necessarily size. Now, more importantly, when we have the same shape, the ratios of the side lengths are going to be equal to one another. So if, for example, I had a right triangle that looks like this, and then I had another one that looked like this, and let's say that that's a 60-degree angle, that's a 30-degree angle, those are similar figures because they're the same shape and they're different sides. But let's say that we said that this side length was 3 and this is 4 and this side length was 6. How long is that? Yeah, to get from here to here, we doubled it. So if you double this, this should be 8, yeah. Definitely. So in similar figures, the ratio of sides is equal. So if this is 1 to 2, this will be 1 to 2. If this is 5, how long would this hypotenuse be? It's going to be doubled, yeah. Yeah, it's going to be 10. So everything's going to be twice as long. You know, if you had a square, and those side lengths were 4. And you had another square where these are 8. Maybe that's not a very nice square, but everything is going to be a 1 to 2 ratio. Everything's going to be twice as long. So how do we set that up mathematically to solve more complicated problems? With this situation here, let's look at what we had. We didn't know that this was 8. But we knew that 3 compared to 6, like 4 compared to some unknown number. So if 3 is to 6 as 4 is to x, we can use what we did in the last lesson with proportions to solve this. So 3 times x is equal to 6 times 4. And if you divide by 3, you divide by 3. 6 divided by 3 is 2. 2 times 4 is 8. So that's what's going to be the length. So we're going to use proportions to solve similar figures. Flip your paper over. So here's a different triangle. Like sometimes it works, and so, there we can see it. Okay, I know it's crooked, but that's okay. Okay. So if we have to figure out how many centimeters side AB is, so here they're saying find x, the length of segment AB. Set that up, solve it. So when you write your fractions, one fraction can be written with one corresponding pair. So this side of my triangle up here corresponded to the 6. Which side corresponds to AC? DF. So if I was going to write out AC is to DF, then you have to take a look at the other two sides that we're working with. In your fraction here is going to have to include, if AC comes from the first triangle, you have to write the other side of the first triangle above here as well. So this will be AB to DE. Now we don't always have to write that down, but we have to recognize it so we know where to put our numbers. So length AC is 5 centimeters. Length DF is 3 centimeters. And then over here, length AB is X. And DE is 4. So here's a proportion where they wrote it down below. They wrote it a little bit different, didn't they? So when they say 5 over x, take a look at this. They're doing this side compared to another side within the same triangle. So if you begin the proportion like this, which you can also do, so there's more than one way to write it. But if we compare 5 to x, then we have to come over to this triangle and come up with a relationship of two sides. that is similar to this relationship. So which two sides could you write the rest of this proportion from? What?
3/4.
3/4, yeah. So here's another way to write it. Now take a look at the first one that I wrote up above. 3 times x is equal to 5 times 4. And if you look at the one that they started for us, here's your 3 times x and your 5 times 4. So you get the same multiplication to solve. It's just a matter of how you look at this relationship. So do you remember doing this with us in 8th grade? We did this last year. Yeah. I have a hunch, though, that we did during COVID time, during COVID learning. Pretty sure that we did. Okay, so solve this. 3x equals 5 times 4.
5 times 4 is 20. 20 divided by 3 is not going to equal 6.6.
Yeah, so that's going to be equal to 6.6 repeating, which is the same as 6 2/3.
There was a 7 when I did on the calculator, it was like 10 sixes and like 7.
Yeah, you're right. On the calculator, it's going to go 6.66666, and then it goes to a 7. These calculators, when there is a repetend, they round up for, if it can be rounded up at the end, it rounds up. Whereas if you do 1/3 on the calculator, the 3 does not cause a rounding up, so it just goes 0.3. And these calculators, if it ends in a 5, it will round up. So it doesn't do that one way or the other kind of rounding. Take a look at this one here. So you need to find the height of that building. So we've got similar figures here. We have 2 different triangles. And we know that they're similar because this triangle that goes through the tree and comes over, this angle is the same as the imaginary triangle that goes all the way over to the base of the building and to the top of the building. So imagine if you were like laying on the ground and you were looking up at the tip of the tree and you lined it up with the very top of the building, and then you measured how far away you were from the tree and how far you are from the building, then you would have 2 similar triangles. And we can use this idea of means and extremes. We can use the proportion that we set up to find out how tall the building is. So you might be able to measure the tree, but you don't measure the building quite as easily. So how would this get set up? Two fractions set equal to each other every single time. Somebody, anybody, help me out. How do you set it up?
Just spit out a guess.
Well,
Wouldn't you do 10 over h?
so you do 10 over h. So you're going to take the height of the tree, and you're going to compare that to the height of the building. Yeah?
And it equals
So
3 over 8.
10 over h. Oops, this should be a red h. There we go. And what is that going to be equal to, Leo?
3 over 8.
3 over 8. Okay, so if you look at this imaginary triangle, this is your triangle for the building, isn't it? And the triangle for the tree only comes out this far. So if the height of the tree is 10, we want to put the bottom edge of the triangle here. So what number is going to go there?
8.
That's going to be 8 for sure. But then if the height of the building is here, the bottom of its triangle is how long?
That's
gonna be 11, you gotta add the 8 and the 3 together. So they do that with these kinds of problems. So getting it set up, you can see both the numerators have to do with one of the triangles and both the denominators with the other. Both the 10 and the h have to do with the height, and the 8 and the 11 have to do with the base of that triangle. So you gotta keep those relationships consistent. So how are you gonna solve this?
You just do 8 times h and then 10 times 11.
Okay? And then,
That equals 10 times 11, 110, divided by 8, and equal 13.75.
don't forget to put units. 13 and 3/4 feet. 13 feet 9 inches. Okay, now, there's some terminology that comes out of the book that we didn't really talk about. Something called ratios of similitude. These are similar figures. So a ratio of similitude would be comparing the 10 and the h to the 8 and the 11. So when we write up like a proportion like this, we can be thinking of that as a ratio of similitude. It's just another way of naming this comparison of these corresponding sides. So let's just look at number 2 underneath here. And I want to ask you how you think we should set this one up. Yeah, this is number 2 here. So if you're going to write fractions, and for example, we are going to, in this polygon and this polygon, and we're going to compare sides, we have to take a look at a few things. We have to look at where we have corresponding sides like these two here, where we know both of the lengths. And then in this case here is the side which they say side CD is X. That's what we're solving for. And then we have to look back at the other polygon and ask ourselves, which side corresponds to CD? And which would that be? So which side in this figure corresponds, I'm sorry, the side CD corresponds to which side of the larger figure on the bottom? Yeah, LM. So we can think of X in the 12.6 as one fraction when we write our proportion. So in this case here, you could say X over 12.6 centimeters. And now we have to go and we have to pick two sides that correspond to one another where you know both of the lengths. So you could not compare AD to JM because we don't know what AD is yet. Yeah, BC and KL. So the X and the BC come from the small figure, so I'm going to make sure that both of those numbers are in the same position in the fraction. And then, let's see, we have 4.8. Now it's just a matter of solving the proportion. So you take that proportion, solve it for X, and then you're done with that step. So when you're doing your work, make sure you show what proportion you're solving, set that up, and then show all of your steps, including inverse operations, to get your answer. Make sure with the final answer you put the units in as well. So work, page 311, 1 through 12. So you can look back for number 1, the fundamental property of similar figures. So that's back in the second page of the lesson, page 309. So this is a formal way of saying everything that we've been saying. It says, if two polygons are similar. So we said what similar was. Same shape, different size. Then the ratios of corresponding lengths are equal. And corresponding angles have the same measure. So when we looked at, for example, this pair of triangles here, these two angles correspond, these two angles correspond, as well as these. These two sides, these two sides, those two sides. So they have the same ratio. So we're setting up fractions again, fraction equivalence.